for dark matter, but not directly for dark matter, but rather from the dark radiation signal that dark matter may emit if it has dissipative self-interactions. So this sounds a bit esoteric, but I'll argue that this is actually a fairly generic or well-motivated thing. And then we're thinking of a smart name or clever thing to call it, and the only thing we came up was call it dark astronomy, because it's kind of looking for dark starlight in some way. I think it's maybe a bit too cute, so if you have a better suggestion, feel free to let me know. So before I start, please interrupt me at any point if you have questions or want to discuss anything. Okay, so basically I kind of alluded to it, but so if we think, or the way that we have to look for dark matter in the lab is basically that we build a very sensitive particle detector, we place it deep underground or in a mountain, whatever, and we wait for one of the dark matter particles to come in, bump into the detector, and then deposit some energy that then we can read out. Because we're shielded from anything else. We don't expect there to be many of the things that will deposit energy in our detector, so we can be fairly confident that if we see a signal that's coming from the dark matter particles, which is the only thing that we have reasonably getting all the way there. But if you think of it, this is very different to the way that we usually look for visible matter in our galaxy, right? We don't wait, say, for the matter particles or to come and hit us, but we rather look for the radiation that things in our galaxy emit. Instead of sitting down in the mine, we put our telescopes high up in the mountain and wait for instance, photons that the stars and all the things in our galaxy are emitting, and then we know where they're coming from, so we get some also spatial information about like where stuff is sitting in our galaxy. Of course, this is easy because we like to interact with photons, but not so much with dark particles. But this is kind of the main idea. Like, can we do something similar to try and look for dark matter? And in some sense, there's already a way that we have been doing it for quite a while, and this is indirect detection. So the idea here being that if there are dark matter particles sitting somewhere in the galaxy, those may decay or annihilate, and if that decay or annihilation occurs into visible particles like photons, cosmic rays, or whatever, then we can use one of our telescopes to look for the signal. And if we can confidently say that the signal cannot possibly come from any kind of visible astrophysical source, and we can say we discovered dark matter. So this is in some sense one way that we can look for like the dark matter shine, but it's going to be very different to what I'm going to be discussing today. So the idea here is going to be like dark matter, because we know that dark matter is not shining a lot in visible particles. We're looking really for small signals, a little visible light. So what I'm going to be looking for here is lots of dark light. So we assume that dark matter is shining a lot, but it's some dark particle that's relativistic and that may be crossing through Earth like with a very large rate. It's just that it interacts very weakly with us. So we don't just see it in a normal telescope or in a usual way. From here, I think there's going to be three main parts for the talk. The first is going to be like motivating that this scenario is something that is well motivated from kind of the theoretic. Then I'm going to delve a bit deeper into the details of what it takes to actually detect dark radiation, and then I'm going to focus on dark photons, as we will see. And then in the end, I'm going to kind of discuss a particular proposal that we're thinking of, like a particular experimental scenario that we think has good potential to discover this signal. So let's start first with the motivation part. So the whole idea of this is that we want to see how reasonable it is for a dark matter model to result in something like dark light being emitted from the galaxy and reaching us. And of course, the first ingredient that we need for that is for dark matter to have some sort of self-interactions. And that is something that by now is not so exotic at all. That's something that people have been considering for a long time, both kind of from the theory perspective, but also from the observations. So the Wordsworth claims that there are some observations of the dark matter distribution in galaxies and galaxy clusters that do not quite match with the collisionless cold dark matter paradigm, in which dark matter is just a single particle that doesn't interact or does anything else. It is not relativistic, and that maybe the existence of dark matter self-interactions can improve the agreement between predictions and observations. It's not so clear whether that's the case. Like, some of those kind of disagreements have been found to just be from mismodeling of the baryonic side of things. But maybe there's still something there. I'm not going to get into the argument. And on the other hand, we know that there are constraints for how strong the dark matter self-interactions may be, because if they're so strong, for instance, very famously, like in the bullet clusters, when two dark matter halos are passing through each other, if they're interacting, they would not pass through each other, as we seem to see here, but they would drag behind. And also, strong dark matter self-interactions could affect the way halos look in a way that we do not really see. So this is just to say that dark matter self-interaction is something that has been widely studied, and there are both constraints and maybe even some hints about their existence. But just interactions themselves are not enough. We need a particular kind of interactions for dark radiation to exist, and that is that the interactions cannot be elastic, but they need to be inelastic, and in particular dissipative, right? Because so when some radiation is being emitted from the dark matter particles, those will cool, and that's what we call dissipation. That's something that we know very well from the baryonic side of things, and that's something that may also be there for dark matter. So this is something, for instance, that's pretty generic in dark sector scenarios, when we kind of acknowledge that we have no reason to believe that dark matter is just a single particle. When we see, a lot of very complex dynamics and many different particles and interactions in the standard model. So the same thing may be the case for dark matter. And in those cases, when we start having multiple particle species and interactions, then it's very generic that some sort of dissipation processes will be there in the theory. And I will discuss now in a minute, like a few more concrete scenarios, how this can be realized. But from the observational perspective, you may wonder how crazy is this? We know that dark matter is mostly, cold and collisionless. But in fact, current constraints only still give room for about even a bit more than 10% of dark matter to have strong and even strongly dissipative self-interactions. You may be thinking that this is not a significant number, but if you remember that dark matter is 5 times more abundant than normal matter, then these numbers are putting us on the order of an amount of dark matter that has a strong dissipative dynamics that may be close to or as abundant as the visible matter in our galaxy. Right, so this can be a significant component of the dark matter. Okay, so as I was saying, so once we've kind of warmed up to the idea that this is not something that's completely excluded or something that's completely unreasonable, we can look at a few concrete proposals that people have done over the years for how dissipation may arise. So maybe I would say kind of the easiest scenario, even almost kind of toy model-like, is the case where dark matter has an excited state. So let's assume that dark matter is made up of the dark matter particle has 2 states that have a very small mass splitting. There's a ground state and then an excited state. Then when 2 dark matter particles, say in the ground state, bump into each other, they can be upscattered into the high energy state. Then if the mediator that mediates these self-interactions is lighter than the mass splitting, then the excited state can de-excite and emit one of these mediators, which would then be kind of a dark radiation particle. So this is a scenario that has been proposed a while ago, and people have been looking at it. For instance, 2 years ago, some people did some simulations for galaxy formation with a model very similar to this, and they found that the way that the dark matter halo looks can be pretty different in the case for these inelastic self-interactions than in cold dark matter. So
because of the existence of this dissipation, I think what they find mostly is that, in the same way that the cooling processes in the visible galaxy makes matter fall towards the central position of the halo, the same thing happens to here. You see a halo that's more compact and more dense in the center. So this is a first model. Then another class of models where dissipation generally arise are strongly interacting in dark sectors. For instance, here dissipation can occur through bound state formation. Say if there's some strong interaction that forms kind of nuggets of dark matter particles, and then two of them can merge together into some excited state, and then de-excites by emitting like some light particles that wouldn't be then the dark radiation, and the details really depends on the exact construction, but that's the main idea. Also in confined theories, you get a lot of states, and some of them may be light, like blue balls or light mesons, and they may behave as, they may be emitted in self-interaction processes as dark radiation, right? Like for instance, just to do some publicity to a paper that we did a while ago, where we had a confined dark sector with an unjoined scalar, basically that we devised a model of a composite dark photon, right? So this composite dark photon that mixes kinetically with the visible photon may be a dark radiation particle, as an example. But there are many different possibilities for, or many different implementation of this idea for strongly interacting dark sectors. So we may also want to look at things that are a bit closer to what happens in the visible sector in the standard model, in which the dissipation occurs through basically something like a gauge interaction with a light or massless mediator. So here's kind of the simplest model that one can think about, just a model with a dark electron and a dark photon. So basically just some dark matter particle that's charged under some dark U1 force. And then we have these different inelastic processes that can occur, like quantum scattering with some dark photon lying around, or Bremsstrahlung processes that, again, generate dissipation and dark radiation. And the people here that studied this model found that this leads to interesting dynamics, like gas fragmentation, the formation of compact objects that start to look very much like what we see in the visible world, right? In fact, this is something that people here at Queen's had looked at quite exhaustively, right? Because all these dissipation processes lead to complex cosmological dynamics, like, for instance, the formation of compact objects. So this is a plot I stole from a paper by Joe, Melissa, and Leo, I think, where they were looking at the size of kind of the compact objects that can form in some of these scenarios. So you can see the trajectory. You start with some overdensity, and then it cools, and it becomes more dense. And I guess all this path depends on the exact implementation of like the cooling mechanisms that you have, but you can make some prediction for what kind of size and density of your compact object you end up with. And in all this process, this thing, depending on the model, may be radiating away energy in the form of dark radiation. Okay, so we can go another step ahead forward into like having a dark sector model that's even closer to what we have today, like we have in the visible sector, sorry. And this is the atomic dark matter paradigm. So this is kind of also a simplified model where, in addition to the dark electron and dark photon that we had before, you add a dark photon, and then kind of hell breaks loose here because you're able to form bound states once you have two particles that have opposite charges under this force, and then you have like a whole lot of different cooling channels, like, well, basically like we have in the standard model, right? Like you can form molecules, you can have many different excited states, etc., etc. So again, this leads to very rich dynamics that people have put on a computer and see and try to look at what happens. And again, they see a lot of of these effects: gas fragmentation, formation of compact objects. You see, so this is what kind of this shows like cold dark matter versus this atomic dark matter. This is what the visible galaxy looks like, and this is what the dark.
The key difference to, for instance, what stars, how stars behave in the visible sector is that here there are no nuclear reactions or anything that can sustain or can produce heat when these compact objects form. So what they happen is that they form something like a red dwarf where matter collapses and then just cools over time. But this cooling can occur over, say, billions of years, and in the process, of course, will be emitting this dark radiation in the form of dark photons as it goes. Even one step further, like I think as close as you can get, is to say, what if the dark sector is just an exact copy, a situ copy of the visible sector? And you may think that this is very ad hoc, but it's actually something that people like from theoretical arguments related, for instance, to the hierarchy problem and the mass of the Higgs. This is one way one can control like radiative corrections to the Higgs mass. By having like the dark sector be an almost exact copy. And here now we have even more complex dynamics in the dark sector. We can have things like dark Big Bang nucleosynthesis in the same way that we have Big Bang nucleosynthesis in the visible sector. And now we open the door to having something like nuclear fusion in the stars, in these dark stars that form. And once you have this, then this could significantly boost the luminosity in dark photons of the dark stars. So kind of this is a bit of a quick review of like some of the ideas that people have proposed for how dissipation may appear in the dark sector. So I'm not gonna buy into any of these concrete models, but what I'm gonna take away is that there are very well motivated and scenarios that are being studied in which dissipation occurs, and dark radiation is kind of ubiquitous in these models. So now what I'm going to be worrying about is, like, again, can we ever hope to detect this dark radiation in experiments that occur? Of course, the answer to this question depends very much on like what is the particle nature for this dark radiation. These dark radiation particles may be scalar particles, they may be pseudoscalars or exonite particles. They may be composites, as I was discussing before, mesons or glue balls. They may be gauge bosons if there is some sort of dark force. So there are many different scenarios. And I'm going to be focusing in just one particular one in the case that the dark radiation particle is a dark photon. In some sense, this is kind of a well-motivated case. So if there is a gauge force in the dark sector, then you will get some sort of something that looks like a dark photon. So, then one could think of generalizing to other cases. And we can discuss more about that if you're interested. But for the rest of the talk, I'm going to just be assuming that this dark radiation is made up of dark photons. So, if there's any question or any comment at this point, if not, I'm now going to move on to a part that's slightly more technical. So,
I do have a question.
Yes.
So, very naive understanding of this stuff is that if you have dark gravitational particles, okay, in this dissipation, you end up forming disks. Except for the Milky Way is a disk, right? From the galaxy is a disk. So there's all this. Does 10% of the dark matter sit in a disk as opposed to? I mean, the reason why you have why people think they have a halo like that is right. There's no dissipation, so you can't get rid of the angular momentum, so it has to just form a ball. But these things would presumably have ended up in a disk. Right?
Yes, it's not necessarily a disk. We also know that there are galaxies that are kind of spherical and different things, right? So, but a disk is definitely a possibility and something that people see appearing in simulations like here.
Okay.
So, yeah, exactly. Like a significant fraction of the dark matter may be sitting in some disks, that. That's in the Milky Way, and like some balls. Depends a bit on like exactly here depends on the gritty details of like how fast cooling is and many details of it. But yes.
Forward went a little bit, but maybe you could just comment now on whether or not the class structures residing in disks will matter for the analysis or to find.
Yeah, so I'm going to be in the end very agnostic about how the dark galaxy looks like. As you will see, in fact, kind of my benchmark model is just going to be like, I'm just going to assume that like most of the luminosity of the dark galaxy is sitting somewhere near the galactic center and has a thermal spectrum. It's a good question, and that's something that would be interesting to see actually, if you have like some kind of more extended structure or something like that, how that affects the analysis. And this ties very much into something that we'll discuss, and is that whether your experiment can be directionally sensitive to the origin of the signal. Yeah. So I will hopefully talk a bit more about that. Well, I will not talk. I will not get into details, but I will say what we assume for this. Yeah. Okay. So we say here a slightly more technical part about like how dark, like how can we detect dark photons in an experiment? Basically, in a visible medium. I'm gonna make a summary in the end, so I don't. If this is not clear to you in the way, hopefully I'll make a summary. So, of course, like we've assumed now, or let's assume that dark matter may have dissipation. It may be radiating dark photons. So one of the possibilities is that if dark matter is completely secluded, those dark photons do not talk to us except gravitationally. Then, well, that's like same as if the dark matter particles do not talk to us. But there is a kind of very natural way in which dark photons can interact with visible matter, and this is through kinetic mixing, a kinetic mixing interaction. So this is an interaction that looks that basically couples the kinetic terms of the dark photon and of the visible photon. And this is something that arises, for instance, if in your complete theory there is some particle that may be very heavy that is charged under both the electromagnetism and whatever dark gates group is mediating this interaction. So this kinetic mixing is usually parameterized by the kinetic mixing parameter that I'm going to be writing as epsilon here. You may have seen that some people prefer to call it chi or kappa. It's the same thing. But in practice, the main consequence of the existence of this kinetic mixing is that it makes the kinetic terms for the photon and for the dark photon not diagonal. So I'm trying to illustrate this here. So the main idea, or the way that I picture this is that, so once you have a dark photon and a visible photon, so you have basically two particles with the same quantum numbers. So any linear combination of those is photon still. Maybe not completely dark, not completely visible, something in between, but that's something that you can think of because they have the same quantum numbers. So in some sense, you can think very kind of geometrically or linear algebra, in a linear algebra way about this, where you have a 2D plane of possible directions that correspond to different combination of dark and visible photons. So what happens when you introduce this kinetic term is that the interaction basis, so the two directions in this two-dimensional plane that give you the direction to which dark charges couple to and the direction to which visible charges couple to are not orthogonal to each other because of the presence of this kinetic mix. But if you want to study the propagation of photons, then you want to have an orthogonal basis to describe these two states. So you can go and slightly rotate one of the two in order to get an orthogonal basis. So of course, you can do this in many different ways. Basically, there is no true symmetry that you can rotate around, but there are two particularly convenient choices. One is the case in which you rotate the visible photon field exactly slightly to make it orthogonal to the dark photon field. And in this case, dark charges only couple to the dark photon, but visible charges couple to a linear combination of visible photon and dark photons. This is something that people call the standard model Milli charged basis. So basically in this basis, you can think of it as dark matter having a very tiny charge proportional to the kinetic mixing parameter. And you can also do kind of the other way around. You can rotate the dark photon and end up with a dark matter Milli charged basis in which to describe the propagation. in which the dark matter has a small electric charge. Of course, at the end of the day, when you calculate any observable, it doesn't matter what basis you choose, you end up with the same answer. But often it's particular to think in one of these two bases when thinking about what happens. So with this, we can really see what it takes. I start to see what it takes to detect massless dark photons. So say that we have our dark galaxy sitting over there that it's shining in wherever it couples to, right? So let's say we're in the dark matter millicharge spaces in which dark matter has a small electric charge. So when the idea is that what a dark particle is emitting when it emits radiation is not a dark photon, but it's a linear combination of something that's mostly dark, but has an epsilon fraction of visible photon, because again, it has this millicharge that's proportional to the kinetic mix parameter. And always, I'm going to be thinking about very small kinetic mixings, because the bounds on these things are going to be at the level of 10 to the minus 9 or ridiculously small numbers similar to those. Okay, so the first thing you can think of is, okay, and you can think really of this probabilistically as in 1 every 1 over epsilon times the dark matter is emitting a normal photon instead of a dark photon, right? So you can say, okay, we can directly point our telescopes and try to look for this 1 every many times in which the dark matter emits a visible photon. Of course, that's a great thing to do, and you can do that. The problem is that, well, where this dark galaxy is sitting, it's exactly where our visible galaxy is sitting, and you know, the visible stuff is emitting almost 100% of the time visible photons, so it's likely that you'll just be overwhelmed by foregrounds. So it's very hard to say, you know, this very tiny signal to distinguish it from all the astrophysical processes from baryonic matter. So then you may think, okay, let's go underground. Let's get rid of all these foregrounds. Well, you can do that, but then, you know, if you sit underground, you'll also be blocking the visible component from this, from the emission from the dark photons. So the only thing that will go through is the completely dark component, and visible matter in this basis is not charged under this. So it will just go through your detector. So either you deal with all the foregrounds, or basically you have no signal. So this sounds a bit disheartening, and you know, for massless, and this basically tells you that it's very hard to detect massless dark photons. However, dark photons need not be massless; they may have a mass. We know that, you know, many of the gauge bosons in the standard model have a mass, and there are natural ways like Higgs mechanism or Stuckelberg mechanism to give a mass to these dark photon fields. So let's assume that indeed dark photons have a mass and see what happens then. So if we add a mass term for the dark photon, now what we have is that we're singling out special direction in this kind of two-dimensional field space, because the mass is going to be aligned with the direction that the dark charge is coupled to. So now there is a preferred way to diagonalize the system to make to get two orthogonal fields, and that is the propagation basis. So the basis in which the two photon states have well-defined masses. So if you do that, you end up with something that's massless and something that is massive around the direction of the dark, like the state that the dark charge is coupled. And this, it sounds like this may not have that much, but indeed what we're having here is, you know, we have we have something that's very similar to what happens in the neutrino case. We have a difference between the mass basis and between the interaction basis for these two states. And this means that this will lead to photon-dark photon oscillations, very similar to what happens to neutrinos. So indeed, this is what occurs. And if we're in vacuum, then we have, like, we can write some oscillation probability formula that I wrote down because it looks very similar to what you may be familiar to from neutrino oscillations. So this is the probability of a dark photon to oscillate into a visible photon in vacuum. So the total amplitude is proportional to the kinetic mixing parameter squared, and then there's this sine squared term that depends on the mass of the dark photon, the energy of the radiation, you know, the length along the travel path of the dark photon. So very similar to how neutrino flavor oscillation works. And now we see that this gives us a way to detect dark photons after shielding, because so let's assume that things start as before. We have the dark galaxy that emits mostly dark, but sometimes visible photons. We place some shielding and stop all the visible things. So right after the shielding, we have something that's a flavor eigenstate that's completely sterile. So it points in like, it's something that dark charges couple to and standard models do not see. But if we go like a distance away from it, or the order of omega over m squared, then these oscillations will occur and will regenerate a small portion of the visible component, which we can detect. So this is something that indeed has been used in the past to design experiments to look for dark photons. So we will see people have been mostly focusing on dark photons that may be produced in the sun, and I will talk a bit more about that. But this is kind of a well studied area, or a well-studied possibility to way to detect dark photons. Some small thing that I didn't mention. So far I was always talking about transverse dark photons. But of course, once we add a mass to the dark photon, then we have a third degree of polarization, the longitudinal polarization that I have not discussed so far. So what happens with that? So longitudinal modes. So in this case, the dark photon. So in this case, we have a massive state and a massless state. The visible photon is massless still. And the dark photon have a third degree of polarization, but in this case, no oscillation can occur just because the longitudinal component of the dark photons has nothing to oscillate into, because the visible photon does not have a longitudinal component. So what this means in practice is that for longitudinal modes, when the dark photon has a mass, there is only one really propagating massive eigenstate, and that is whatever, the linear combination between dark and visible photon that has a well-defined mass. So this means that even if we place any shielding, if we have vacuum on both sides, the only thing that can be propagating is the same thing that we had before, this linear combination that has a mass and therefore can support a longitudinal polarization. And this means, in practice, in particular, that longitudinal dark photons cannot be shielded. So in comparison to transverse modes, where we have to wait for this distance in order for the small visible component to be regenerative, for longitudinal dark photons, this is not the case. Straight after whatever shielding we place, we have a visible component, just because this is the only thing that can propagate as a longitudinal. And this is relevant, or will be relevant in practice for experiments. Okay, so this is, so far I've been discussing what happens kind of in vacuum, or maybe if we place some shielding in between. But if we want to think about detecting this in the experiment, or in some, in some experiment, we're not going to be looking at things propagating in vacuum, but things propagating in whatever material our detector is made. And that has, again, an important impact in this, because in medium, photons are not necessarily massless. They may acquire an effective mass through refraction effects in the medium. And this basically generates also an effective mass in this direction. Then again, has an impact in how we diagonalize and find the propagation eigenstates. So one can go through the diagonalization and find the eigenstates, and when one finds kind of what one could have expected, now we get two massive states, because of course both the visible and the dark photon have a mass. We get something that's very close to a visible photon, and if it's in a medium, it's something that gets a medium that's opaque, fairly opaque to this. It's something that gets absorbed pretty fast. So at a similar rate to how, basically the same rate at how visible photons are absorbed. So it depends on the real part of the conductivity, the imaginary part of the refractive index, whatever you want to call it. And we have another state that's mostly sterile, but not quite so, because it gets a small admixture of visible photons, and then there is this small probability for it to be absorbed. So this means that, say, if visible photons have a mean free path of a micron in whatever material you're thinking of, then the dark photon will have way longer mean free path, something that's like, I don't know, 20 orders of magnitude longer than that, but still something that gets absorbed at this slow rate in the material. So I'm going to go a bit quickly through this, but so I want to focus on the next thing first. But this, now inside a medium, the oscillations, the dark photon-to-photon oscillations can be resonantly enhanced. So for transverse modes, this occurs when the effective photon in medium mass matches the mass of the dark photons. So this is something that in dielectrics does not happen because this quantity is negative, but in a conductor where this effective mass is equal to the plasma frequency of the material is positive, then this resonance can occur and amplify the oscillation probability significantly. And the other consequence of being in a medium is that now we can have longitudinal oscillations because conductors support longitudinal photon modes. These are what we call plasmons. They're just kind of really pressure waves of electrons in the material, but they behave like effectively like a third polarization for the electric field, just with a weird dispersion relation. The dispersion relations of plasmons, at least in a perfect conductor, are just frequency equal to the plasma frequency of the material. But the important thing is that now we have something that the longitudinal dark photons can mix with and oscillate into. And again, resonance is possible. This time it occurs when the plasma frequency equals the frequency of the incoming radiation. And in practice, the most important thing is that the amplitude of the oscillation is enhanced for longitudinal modes compared to transverse modes by this factor of omega squared over m squared. So the frequency of the radiation squared over the mass of the dark photon squared. So in the case where this mass is small, then this can result in a significant enhancement that tells you that it's probably easier to detect longitudinal modes than transverse modes in a material. Okay. And then another thing that will be relevant is, what happens when a dark photon comes from vacuum and enters like a visible medium, like maybe our detector. So what we said is that in the medium, we can distinguish two propagation eigenstates, one that's mostly sterile and one that's mostly visible. So of course, dark photon, the overlap of the dark photon with the sterile state is close to 1, except up to corrections of further epsilon squared. And the visible component is tiny, just at the level of epsilon, but these two components behave very different. Whereas the sterile eigenstate, we've seen that gets damped at a very slow rate, and therefore leads to some volume absorption signal in the material. The visible component gets damped very fast, within one absorption length for visible photons of that frequency, and therefore leads some surface signal. That's going to be something that we will be using later on. Okay, so this is just to say that, when we have a mass for dark photons, then we have a hope to detect them in underground experiments. So this was kind of the technical part. So a quick summary. So we've seen that massless dark photons are tough because no signal remains after shielding, but when we have a mass, transverse modes oscillate, and even better, longitudinal modes cannot be shielded. We have a chance of detecting massive dark photons. And in a visible medium, we can distinguish two propagation eigenstates, one that's mostly visible and that can lead to surface signals in a detector, and one that's mostly sterile that leads to volume absorption in a detector. And we're likely better off looking for longitudinal modes since their absorption rate is enhanced by a factor of frequency over the mass. Okay, so now we go on how can we use everything we've learned about these dark photons in practice. So now what we want to do is go back to say, okay, so what are the astrophys that we may want to, of dark photons that we may want to look for? So as I was saying, the sun is a source of dark photons, because in the same way that dark photons can oscillate into visible photons, the transfer process is also possible. Visible photons can oscillate into dark photons. So this means that any source of visible photons is also a much weaker source of dark photons, and the sun is the strongest photon source that we have. So, this is something that people have looked, and in particular has the advantage that you do not need to assume that these dark photons are connected to dark matter in any way. They will reproduce in the sun no matter what. But this is not the signal that we're interested in, really. So the sun is going to be mostly a foreground for us. So we're going to be more interested in the emission from the dark matter in our galaxy that we were discussing first. So I will call this, the dark galaxy signal, dark starlight, dark radiation. So I'm going to use all these words indistinguishably. And just a quick word that they may also be some cosmological sources for this, but they require some model building because it must comply with constraints from the number of relativistic freedoms at BBN and CMB times, for instance. So there are ways to model build around this. I'd be happy to talk more, but I don't want to get into those today. So I think in the interest of time, I will not say much about solar dark photons. The main key thing is that this is the production of dark photons in the sun is something that has been done for many years now and is well understood. So as a function of the dark photon mass, we know what the spectrum of dark photons we could expect from the sun is. And the main takeaway is that the emission is predominantly in longitudinal modes if the dark photon mass is small. It's enhanced again by this factor of omega of frequency squared over mass squared. So people have looked and placed bounds on this signal based on the absorption of solar dark photons at dark matter experiments. And this is what the current bounds look like. So as a function of the dark photon mass in the x-axis, here, these are the bounds on the kinetic mixing parameter. From like the two leading experiments, kind of, XENON 1 ton, this is the kind of experiments with the most exposure and therefore puts the strongest bounds. But then I've also chosen to show how SENSEI could do as an example for an experiment with a lower threshold. And you can see that right now it's not competitive compared to XENON 1 ton just because of the luminosity difference between the two. But as SENSEI goes and collects more data, it's going to be able to in some region of the parameter space at least beat the XENON 1 ton bounds just because of its lower threshold, because it can access a kind of a lower region of energies from the solar spectrum. So this is just, we need to understand well the emission from the sun because it's a potential foreground for our search. But what we really want to look at is the dark galaxy emission. And here, this is where I address kind of the question that Joe was asking. So basically, the details of the spectrum from this emission is going to be very, very, very model dependent. So since we want to do a fairly general analysis, what we decided to do for this case is just parameterize the signal as a black body spectrum with a given temperature and luminosity, and assume that it's located at the center of the galaxy, so 8 kiloparsecs away. We also assume that the signal is dominantly longitudinal, and there are reasons for this that I can get into if you want, but if you can also otherwise think of the bounds that I'm going to be presented as bounds on the emission of longitudinal modes from the dark galaxy. Okay, so in terms of these parameters, we can compare the emissions from the sun and from the dark galaxy. So here, as a function of dark photon frequency, the y-axis is the differential flux factor. So as I was saying, for the sun, this is very well understood. Here I'm fixing the dark photon mass. So, this is the longitudinal emission over here. That's overwhelmingly dominating compared to the transverse emission for the mass, I think, of a milli-electron volt that I'm choosing here. And this is, and this is overlaid with what we could, I don't know, guess the dark galaxy may be emitting. And this is just saying, say if the dark galaxy has a temperature equal to the temperature of the sun and a luminosity roughly equal to the luminosity of the visible galaxy. So this would be what it would be doing. And if the dark galaxy was 10 times as hot as the visible galaxy, then the luminosity would be somewhere over there. So these are just some kind of arbitrary benchmarks to compare it. So the key thing here to see is that solar emission decreases at epsilon squared because it's visible through oscillations of visible to dark photons, whereas the dark galaxy emission does not depend on epsilon at all. So as you lower the value of the kinetic mixing, and so say your experiment is getting better, it's accessing smaller values of the kinetic mixing, then the possible signal that you can see from the dark galaxy over the solar program is winning, right? So you gain like smaller values of the dark galaxy luminosity become accessible over the solar program. Okay, so then we can do the same exercise as we did for the sun and say, so what kind of luminosities would these experiments, XENON, McDonald, and SENSEI, be sensitive to? So as a function of the black body temperature of this hypothetical emission, this is the kind of the smallest luminosity that we could see given the bounds on the solar foreground. And again, I can get into details to how this plot, how like what assumptions go into this figure. But basically, you can see that right now experiments would be sensitive to luminosities at the level of 10 to the 16, which is way larger than the luminosity of the Milky Way, which is at the level of 10 to the 10. But the bounds or the rates can significantly improve with exposure for the SENSEI experiment and go down to 10 to the minus 10 to the 13 solar luminosities or so. So this is what we can do, or what current experiments are sensitive can do with respect to dark radiation. But then what we wanted to think is like, can we do better? Is there a better way to detect dark radiation than that, just to use the dark matter experiments as dark radiation detection? And kind of a way, or a clear way that we could improve is we could get some directional information. Because the signal is inherently directional, right? Like dark matter is shining from somewhere and it's getting to us from some particular direction. The problem is that these dark matter experiments are not really optimized to have any directional sensitivity. But directionality would have to reject backgrounds, confirm the origin of the signal. Say if it's really the sun, you could tell whether the signal is coming from the sun or not. Mitigate the solar foreground for the dark galaxy search, and if you get optimistic and get a signal, even map where the emission is actually coming from in the galaxy. So maybe some experiment with an anisotropic target could be used to get some directionality. But what I'm going to be arguing here is that there is a simple way that we can exploit the surface absorption that I was discussing before, rather than the volume one that like dark matter experiments rely on. So this is this surface conversion that I was describing before. If you remember, when a dark photon enters the material, it splits into two propagation eigenstates, one that is absorbed very near the surface, and one that goes through and is slowly absorbed throughout the volume of the detector. So now, if we design an experiment in which the target is some thin plate whose one dimension is much larger than the mean free path, of photons, whereas the other one is much smaller, then we can have directional sensitivity, because if we place this plate face on towards the origin of the signal, then the surface absorption will occur all throughout basically the volume of the material. Whether if we place it edge on, it will only happen in small region of the material. Because basically all the signal will die here. So you can also think of this, as a geometric flux thingy. So basically, with this geometrical design for the detector, you can have a signal rate that's basically proportional to the cosine of the angle to the origin of the signal. So you have some directional information. So now the question is, do you lose anything by using this resonant, this smaller part of kind of the dark photon instead of the larger thing? And the answer is no, because per unit volume, the absorption rates, say within the first mean free path, for the volume and the absorption processes are very similar to each other. So this is what I am showing here. The absorption rate, like some kind of arbitrary units as a function of dark photon frequency for silicon and copper. So if you remember, I was telling you that this absorption process is resonant around the plasma frequency of the material, and copper has a plasma frequency of around 10 eV, so this is why it's so sharply peaked. Silicon is a worse conductor, but still has a plasma frequency around like 16 eV or so. But the fact that it's much worse conductor is that it has a wider resonance. But like the thing to notice here is that these are the rates for the surface volume, for the surface absorption and the volume absorption. And you see that the two are very similar. So they're going to lead to like gram per gram, very similar absorption rates. The only thing is that one will occur at the surface, the other one in the volume. So then this is kind of, we can take advantage of this if instead of using a big chunk of silicon as our target detector, we can use small thin plates of it. In this case, we're going to be using copper because of the fact that it's a better conductor, gives you better, basically makes it easier to, well, like copper is good because a better conductor at the frequencies that we're interested in, the plasma frequency has a longer mean free path. Yeah.
I just some good questions. Maybe I just lost track of.
Yeah.
So you had the argument that the longitudinal node goes through any building, so that's fine.
Yeah.
So now it's in this resonant surface, but you can capture some of the transverse.
No, longitudinal. It's all longitudinal.
It's all on.
Yeah, sorry.
But it's just you're getting resonant conversion of longitudinal.
Yes, exactly. It's resonant conversion with longitudinal nodes. Yeah, I guess that was a bit confusing. Sorry. Because here that's why I'm looking at conductors, because conductors have plasmons, and then the resonant conversion is dark photons into plasmons, and then the plasmons get quickly or not so quickly absorbed. That's why in copper, pure copper and cooled copper, the plasmons have a longer mean free path, and this means that we can have detector targets that are at least kind of the order of millimeter thick. If we looked at silicon, where plasmons get absorbed much quicker, then we would have to make very thin, very thin target materials. That's more impractical. Yeah, but this is the main idea. So the advantages of doing this is that now you have directional information, and also if you're using copper, you get the advantage is that you have no threshold in your experiment compared to a semiconductor, for instance. But there are challenges too, in particular the readout and the purity of copper that you need to reach these mean free paths. So I'm gonna just in the last few minutes argue that this is this is something that can be made to work. So in particular with regards to the readout, so the goal here is to read out 10 eV energy depositions, and 10 EV is just because this is the plasma frequency of copper. The strategy that we decided to use is to use volumetry. This is similar to what's done, for instance, in super CDMS. And the challenge is the fact that conductors have a much larger heat capacity than a semiconductor. So this means that the same amount of energy results in a much smaller temperature increase in a conductor than in a semiconductor. And this is due to the fact that the heat capacity in silicon is driven by phonons, but in copper, it's the free electrons that, get all the, that absorb all the heat. And this is what basically means that at very low temperatures, so this is at very low temperature of 10 millikelvin or so, and the heat capacity of copper is much larger. So this means that, what you can measure here, you're limited by the temperature increase that you can measure, which is going to be much smaller in copper. So this means that your target has to be much smaller compared to what you can do with silicon. But still, you can run the calculation and see that kind of for reasonable operating temperature, say tens of millikelvins, the energy deposition is 10 eV, and assume that you can measure temperature increases at the level of a nanokelvin, then you can use volumes of copper that are millimeter cubed or so, or 0.01 grams of copper. And this is something, so this kind of temperature increases, I think that can be measured using a cryogenically operated transition-edge sensors. For instance, this is something that has been demonstrated, or close to this space, for the Ricochet experiment that's looking for coherent electron-neutrino scattering. So these are numbers that are motivated from what can really be done, and this comes this whole discussion comes after a lot of discussion with Miriam Diamond and Jikin Hong in Toronto. So I hope I didn't just argue that make this all up. Okay, so we think that we have a way to read this signal. So what about the copper purity requirements? So we know that we can have volumes of millimeter cubed as much. So say we make these plates to have a surface area of 10 millimeters squared and a depth of 0.1 millimeters. That gives you a millimeter volume, and an aspect ratio such that if you have a mean free path of photons being around 1 millimeter, then you have what you want, because you're going to get the 1 millimeter be much larger than the side length, but much smaller than the long dimension of the plate. So now the question is, are these 1 millimeter photon mean free path of the plasma frequency reasonable? And for that, we use a simple Drude-Sommerfeld model for the conductor, and taking into account that at low temperatures, the conductivity of copper is driven by impurities, because the photon contribution is subdominant at these very low temperatures. And the conductivity, or the inverse conductivity, which is the resistivity at these very low temperatures, is measured by the residual resistivity ratio, which is just the ratio between the resistivity at room temperature and at 0 Kelvin, when the impurities contribution dominates, and which is roughly temperature independent. And you can see that you need values for this residual resistivity ratio at the level of 100 or 400, which is actually very reasonable for ultra pure copper. So with this, it seems that it seems reasonable to construct this kind of detector, and we can even have an idea for a preliminary how a design may look like. And this is borrowing the technology that has been developed for the transition edge sensor detectors for ricochet, because every single pixel here, which is a single PES, has roughly like an area of around 10 millimeters squared. That's exactly what we want. So it would be just a matter of placing these chips on top of a 3 by 3 millimeter by 0.1 millimeter plate of copper, and then arrange them in whatever way. So here they just put all the chips on top of a silicon wafer, but here each of the individual chips would be placed on each individual copper target. But we can do something very similar to this, and these are operating at temperatures, at millikelvin temperatures, and can detect nanokelvin energy temperature increases. And there are even like some technical things that may be easier to do in copper than in silicon, that I'll be happy to discuss if you're interested. But this is just to say that this seems something that's reasonable, and that could be and where we can use like technology that's currently being used for or designed for other experiments to construct what we want. And then these are the projections that we get for this experiment for the solar dark photon search. So here I'm writing the projection in terms of exposure in gram per days or surface time. So you can see that for solar dark photons, it seems that we do not. Gram per gram, we do something very similar to what SENSEI does, really, because the sensitivity in this case is very similar, but we have the advantage of better background ejection due to the directionality, and the possibility to confirm the signal, whether the signal is actually coming from the sun. And then for the case that we care most, which is the dark galaxy, we see that we do even better than SENSEI here, at least gram per gram. And this is because we now have the advantage of being able to do foreground abstraction. So most likely, if you see a signal from the dark galaxy at the level that we can see now, this would also mean that you would also see a simultaneous signal from the sun. And if you have directionality, you can distinguish both of them, and also give you the opportunities to map the source of the signal. And since I'm already over time, I will sum up here. And this is, I hope I could convince you that dissipative dark sectors are an interesting possibility, and they may be detected not by the dark radiation that they emit, rather than looking for the dark matter particles that make up the dark matter itself. And we have been thinking about new detection processes that have directionality to the signal. And for instance, this photon conversion in a conductor seems to be something that could be reasonably exploited. And I find this kind of new way of trying to look for this kind of dark matter interesting, in the sense that it combines some techniques from dark matter direction experiments, but also some techniques from astronomy, in the sense that you're looking for a signal that may be moving in the sky. So there are things to think about like field of view and things that you can do, and that you can do once you have a reasonable prototype. And this is why we decided to call this dark astronomy. But as I said, there may be a better name for this. So I will stop here. Thanks.
So, quick question about the beginning. I didn't quite get that part. In the beginning, you said that there was some research paper where they showed that at least 10% of dark matter is strongly self-interacting. Do you happen to know how they come up with that condition?
Yeah, well, I mean, that it could be, right? There's no evidence in favor of it being self-interaction, but if you take the bullet cluster and say, okay, I allow for a fraction of dark matter to be strongly self-interacting, like, what are the constraints on this fraction? And this fraction is roughly at the level of 10% or so.
Okay.
So you said that you expect more longitudinal
Mhm.
than at a factor square.
Omega squared over m squared, that's for the solar emission.
Right. Is that due to the shielding or is that just due to some
For the sun, this is due to the fact that the resonances for transverse and longitudinal modes are slightly different. So the resonance for transverse modes occurs when the plasma frequency matches the mass of the dark photon, whereas the one for longitudinal modes happens when the plasma frequency happens the frequency of the radiation. And if the frequency, the mass is smaller than the frequency, this resonance will happen closer to the center of the sun, where you have higher densities and higher temperatures. And then after you plug all these things, this ends up giving you this scaling for
so like
let's see. And for the dark matter signal, the reason we think that longitudinal modes may dominate is because of the fact that longitudinal modes are more weakly coupled than transverse modes. Like if you forget about mixing visible and dark photons, if you just think about, what would happen, how would the sun shine if the photon had a small mass? So if the photon had a small mass, you'd have a longitudinal modes that weakly coupled, and that would escape the sun from the interior, not just from what we see the photosphere of the sun, but from the interior, which is hotter and more dense, and it gives you an enhanced emission.
already at the dark photon axis.
So say if there were dark stars, for instance, then dark stars with a small dark photon mass would shine more in longitudinal modes than transverse modes because of this. Basically, because the transverse mode, because the environment would, if they're more weakly coupled, they're less shielded by the outer layers of the sun, so to say. Or it's the sun or some dark star or like some dark brown dwarf thing. They would escape from the interior where you usually get more emission. Yeah.
So I think maybe you said this. So when you're detecting, so you're looking for these longitudinal modes converting resonantly inside your detector. And that doesn't, because of what I'm seeing here, that doesn't depend on the mass of the dark photon, only on the.
Exactly.
You just need a broadband frequency.
Exactly. That's also another advantage. And thanks for bringing this up. So if you look for transverse modes and you want to have a resonant, then you have to engineer the plasma frequency of your detector to match the mass, but not in this case. In this case, whatever mass it is, you're sensitive to a range of the dark electromagnetic spectrum. So the only thing you need to assume is that, the spectrum is non-zero at those frequencies.
As long as it covers your.
Exactly. Yeah.
Just kind of elaborating on that, so I understand. To get the resonant conversion, it's the frequency of the dark photon that you want to match the plasma frequency in the material.
Yeah.
Yes.
Yes.
Okay. And is there any particular reason that like 10 eV is like a frequency we might expect to see things at?
Not really. That's a good question. We just chose copper because it's a good conductor that you can make high purity and where you can make these things work, but you could use other materials which have a plasma frequency at other frequencies, and then, ideally you do more experiments and be sensitive to different frequencies of the dark electromagnetic spectrum.
But I guess you expect resonant frequencies running around that.
Yeah. So 10 eV, say the sun, the sun is dominantly emitting in a few eV. So say dark stars or dark emission is like a bit hotter than the sun, then that gives you like, but this is just a bit wishful thinking if you want. It's just, you know.
It's in the UV, it's not on the UV.
It's in the, isn't it a few, like 2 EVs or so?
But like if you go a little bit deeper in the sun, you're hotter.
Yes, yeah.
Are there any prospects for developing this to just detect dark photons from the sun? I realize that KV sort of levels, you're probably not going to get better bounds than what's being done on the cast, but maybe lower.
Well, cast gives you worse bounds than XENON. Like XENON gives you the best bounds right now. So I mean, this is things are today. This is what it would take for this to overcome. Right, you need roughly 1 kilogram day of exposure, which is 1 meter squared day, and if say you did something like that, what would you need, like 10 of these or 100 of these? Yeah.
This nano sensitivity ricochet. Do you know how that compares to what Crest was already achieving with their TESs? I know that's a larger volume at least.
Yeah, I'm not sure. So I was chatting with Jigging about this, and he told me that the things they were doing for ricochet seemed like the closest to what we wanted to do. So I don't know the specs about the other experience. Yeah, that's true.
Oh no, I was just curious. I don't know if maybe the experimentalists would know this, like why xenon 110 can see dark photons? And set up to do that.
Well, it's just because xenon will have us like xenon also has a also absorbs photons, right? So anything that absorbs light will absorb dark photons at an epsilon suppressed rate.
An electron recoil search.
Yes. Yes.
Recoil.
All right, well, if there are no other questions, let's thank Gonzalo again.
Questions online?
Thanks,